Yeah, they won't click off your results, they'll make you go online and wait for it.
Last week I introduced you to synchronous bond formation in pericyclic reactions, reactions that proceed through a cyclic electron movement transition state. That's one of the definitions of a pericyclic reaction. They all have cyclic transition state structures where the electrons are simply moving around in some kind of ring system. And you presumably, I hope, got the impression last week that the allowedness, I use the word allowed to describe a reaction that is facile. They're described as allowed, and you perhaps see now, because of my analysis, why I use the term allowed. It's because the orbital symmetry of all the interacting orbitals has to match properly for this cyclic array to have a lower energy state than it would be otherwise if the molecules didn't join together. And I introduce you to the most common example of this reaction, which is a 4+2 cycloaddition, 4-pi component, 2-pi component. These are the carbons which are bonding. The whole thing is driven forward by the fact that it produces 2 sigma bonds, so lots of energy is available in this. I think your notes give you the number, 40 kilocalories per mole. Ancient units, but still works. 160 kilojoules per mole. So there's a lot of energy gained when this thing forms its 2 sigma bonds from what you know to be weaker pi bonds. And I analysed this system in terms of the HOMO of the diene, highest occupied molecular orbital of the diene, which has got that symmetry, and the lowest unoccupied orbital of the 2-pi component, which has got that symmetry. And these reactions are always, the key interactions in these processes are always the interactions of the highest occupied, highest energetically available field orbital, which is called the HOMO, and the lowest unoccupied orbital on the receiving system, which is called the LUMO. Now this analysis has to work in both directions, and so if we take the 4-pi HOMO of the diene and the 2-pi LUMO of the dienophile, as it's called, and we reverse that and look at the LUMO of the 4-pi and the HOMO of the 2-pi, that still works. And I just switch. We've now got the LUMO, psi3 of butadiene here. These two are the same phase, but in the HOMO of the 2-pi in the pi system, in the pi bond, that is also in phase. And so there's in-phase overlap whether we look at the HOMO-LUMO or the LUMO-HOMO interactions. And that's a key component of these reactions as well. Now, I spent last Friday talking to you about the way that the one particular pairing of HOMO and LUMO can be made to predominate. The idea being that the covalent bonding is better the closer the two orbitals are in energy that are interacting. So if you can have a LUMO and a HOMO that are close in energy, that's the best situation for good covalent bonding. And you can raise the energy of a HOMO by adding donors to it, or you can lower the energy of the LUMO by adding acceptors to it, and that gives you the way to fiddle with to tune, if you like, the orbital energies, to get them closer together and make the process more favourable. So that's a summary of Diels-Alder reaction. This is a thermally allowed 4-pi plus 2-pi cyclone. I'm going to extend my definition of allowedness today and introduce you to the alternative, which is forbidden. Sounds much more interesting. And you'll see that allowedness and forbiddenness are basically expressions about the amounts of energy involved in order to make them go by these particular, their respective orbital interactions. Now, if we examine the 2+2 cycloaddition, looked at the 4+2, let's just look at a forbidden process. This is the 2+2 cycloaddition. They're called forbidden processes because of the extraordinarily high amount of energy that you need to make them work. In fact, that's not a very good explanation. The fact is they have to go by different mechanisms. If they can't go by what are called superfacial overlap, synchronous overlap of the ends of the pi system that are reacting, then they'll go by stepwise version instead. They'll go by a radical process. And so when I talk about this forbidden and allowed reactions, when a forbidden reaction is simply forbidden on the basis of a particular mechanism. It may go by some other mechanism. So in other words, there are 2+2 cycloadditions, but they don't go by concerted superfacial overlap, which I'll show you what that means in a moment. So here's an alkene. In fact, we should be quite glad, if you think about it, if alkenes were able ad lib to overlap in a 2+2 manner like this, say ethene reacts with ethene, that X and Y are H, if that was to give us cyclobutane, we wouldn't be able to handle ethene. It would just simply dimerize all the time. Alkenes would be impossibly reactive towards each other if this were not a forbidden reaction. So we should be glad. So what I want to analyse is why it's forbidden. We can draw the picture, we can put the arrows on, and have arguments about which direction we should point the arrows. We can draw this neat little transition structure which has got these pi bonds that are going and sigma bonds that are arriving, so we have a picture like this, so we can draw the product and claim that the cis stereochemistry of the alkene is retained. But the fact is those reactions do not go. And the reason can be understood most readily if you look at the orbitals that you are asking to overlap. So here's ethene with its two components drawn here in the old atomic orbital contributions method, which has the benefit of showing you the correct phases. There's the HOMO and there's the LUMO of ethene, same phase, different phase. Here's another one. Of course it's the same because it's a 2-pi system, whatever X and Y are. We might be able to fiddle with the levels, but we won't be able to change the phases. And so that's going to be the HOMO, and that's the LUMO of this other alkene, alkene 2 as I called it. And if we were to overlap in a bonding way, we would have to have a HOMO of one interacting with the LUMO of the other, and vice versa. And if we look at that, we place these two next to each other and start to form the bonds, then we can do that very comfortably with the LUMO of alkene 1, which has got that symmetry, and the HOMO of alkene 2, which has got that symmetry. We can get so far, we can say, yeah, they're going to overlap nicely, they're in phase, bonding. But look at the other two. We can't actually overlap these because there's an anti-bonding relationship, so there's repulsion. And so that way round it doesn't work. If you analyse the other way round, of course that's not going to work either. There's the HOMO of this alkene. They're in phase now. There's the LUMO of the receiving alkene 2 this time. They're out of phase. Only one pair can overlap with bonding interaction. The other, it's an anti-bonding relationship. And so neither of these reactions can go by superfacial, that is same face addition. And so we say that this is a thermally forbidden reaction. And how to make them work actually is in the clues there thermally. You can't make them work thermally. They're not. It's a disallowed process because there isn't in-phase overlap at both ends of the interacting system. So some terminology is on this slide. I've started to use it. This is we're asking an alkene to react with another alkene. And I want to refer to this as a pi. I want to extend this 2+2, 4+2 business. These numbers usually have subscripts added to explain more, to define more what sort of process it is. And that nomenclature is in common use, so you need to know it. It's pretty obvious. We have instead of just a 2+2, this is a pi 2s, where s means superfacial, and that means the interacting orbitals are on the same face, in this case of an alkene. And this would also be a superfacial relationship if we ask those two to react with these two. So that would be a pi 2s plus pi 2s. The alternative, so definition here, look, when two new bonds are formed on opposite sides of a pi bond or conjugated pi system, as in the ethene component of the above right-hand diagram, we could ask this thing to do not a superfacial addition, so in other words that not overlap with this but overlap with that one. If we can overlap those two, we would have an in-phase relationship, and that would be a bonding relationship. With that, in this particular picture, this alkene would be said to be reacting superfacially. Both of those orbitals are upwards on the same face. This one is reacting antarafacially. So there's a new word for you. That's when it's the orbital on one side of the pi system, and reacting, the other orbital it's reacting is on the other face. So this piece here is reacting antarafacially, and that's a 2 pi A, or a pi 2A. So that's a thermally allowed pi 2S plus pi 2A. If we can get our two alkenes to interact in that way, it's a thermally allowed process. But let's not forget entropy, because if you'll see in a minute, if you ask an alkene to react like this, antarafacially, that's, turns out, is a rather big ask. So it's so fast to change that you miss it. If the two new bonds are formed on opposite sides of the pi bond, that's antarafacial. So that one is reacting antarafacially. If the two new bonds are formed on the same side, like those two would, that would be said to be superfacial. So those two words are important: antarafacial, superfacial. You'll see them again and again. So the pi 2s plus pi 2a cycloaddition is thermally allowed. Are there any examples? Well, yes, there are, and I'll show you some. But look what's required, and you'll perhaps appreciate how remarkable the examples are. So we're asking an alkene or a 2-pi system to react with a 2-pi system. We know that they can't both react superfacially, because you will only get overlapping with bonding at one pair of orbitals. We have to overlap this in-phase relationship, either that one or this one. Otherwise we have anti-bonding. And so maybe if we ask these two things to approach at right angles. So I've now drawn this with one of the alkenes turned round through 90 degrees in both senses. It's turned around through 90 degrees so that its orbitals are you're now looking down on them. So they're circular, we're looking at from above. And it's lumbering up to the other alkene such that these two in-phase superfacial orbitals could interact with the two in-phase antarafacial. And so if we could conspire to arrange a transition structure like that, then that reaction is allowed. It turns out, as you might imagine, that that's rather difficult. And I think the game is completely given away if you start remembering that these alkenes are going to be substituted. And you're asking them to do something entropically, which they're not remotely interested in doing, which is lumber up to each other, sideways on. And despite the size of these R groups, get together in what is a very confined space and overlap with these overlap the pi orbitals in the right phases. So that particular transition structure is a very difficult one to achieve by just putting two root molecules in a flask and warming it up. So that reaction does not occur, although technically it's possible. Now, if we can reduce the interactions with between these R groups, we have a chance of making this sort of reaction proceed. And that's so this pi 2s plus pi 2a, 2 plus 2 type cycloaddition is known. The circumstances are rather special, but the reactions of themselves are amazingly efficient. I'm a little bit surprised that one of these isn't in the second year or the third or the second year lab course, actually, because it is very instructive. This is a ketene, and one of the ways that we've got, there's our reacting pi bond. Some of you will probably think this is cheating when you see the orbitals that are being used to make this reaction work. But you should agree that since this carbon is sp hybridized, clearly it's very much smaller than it would be if it were sp2 and had a couple of R groups hanging off it. So this end is much smaller. So sterically we've achieved what we might want to do and make the size of this interaction much smaller. These are quite easy to make. You have a chloride, hydrogen on that carbon and a chlorine on there. That means you have an acid chloride. And you can treat it with a base, and you can pull off the elements of HCl, and give you one of those in solution, which you can actually generate that in solution with cyclopentadiene, and the cycle addition takes place. Very efficient, room temperature, 72% yield. One of the things I would draw your attention to is the stereochemistry here. If these are the two products, and you see that the major product, if you were to guess sterically which product would be more stable, it would be the other one. Because look, we've got this one. If you follow this X-ray diagram through, the ethyl group is underneath. So there's the ethyl group, and it's actually in close proximity to the rest of the cyclopentadiene, as was, the 5 carbon piece. The methyl group is pointing out into empty space. Sterically, it would be a more stable entity if it had the ethyl group, the large group, pointing out into space, and the small group tucked under in proximity to the carbons across the way. But that's the way around these things go. But it's not until you go to the mechanism that you can appreciate how that is a natural result. Now, this diagram is in your notes. It's the online version of this. I have to recommend 27 is a must. Go and look at 27. You can see the orbitals in close proximity. Here's the cyclopentadiene, and this is the result of a lot of experimenting with graphics. It's the best I can do to show you how these interact. You really want to make the models to see better. Cyclopentadiene is at the back, and we're looking down on its orbitals, and we're looking at its HOMO. Okay, so in its HOMO, remember, it's got, whichever end you like to start at, it's got 2 the same, and then 2 the other side the same. So that would be white, white, red, red in the HOMO. These are the interactions. This is the LUMO of the alkene if I were to draw it in isolation. Okay, out of phase across the top. So we've got a HOMO there and a LUMO there. And we're going to bond the white orbitals. That one of the alkene just here, and that one of the alkene just here. So that's doing our tricky little transition state with the two things at right angle. When it does that, the small group is pointing towards the cyclopentadiene, and the large group is pointing out into space. So it's in the transition state where that stereochemical decision gets made, and now it's rational. The large group points away from the reaction centre. But if you make those bonds, and I recommend this business of drawing things in the same daft looking picture, but draw it in a way that shows you how it was being built. So you can see that these bonds, there's a bond being formed, this one, there's a bond being formed, that's this one. If you then take that model and unravel it, when you do that, you'll find that the H atoms and the small group are all going to be on the same surface, which I'll turn it over and draw it like that. So there's the H, 2 H's and the S, and they're all going to wind up on the same surface. And the large thing is going to swing round and tuck underneath, and there it is. So that particular odd-looking stereochemistry is a natural result of the particular mechanism where the large group sticks out into space if your ketene unit is unsymmetrical. And some of those reactions, in the link to 027 on the blackboard, there's a link to the original piece of literature. This is from Robotica Chemica in the 1970s, and there's a whole table of results, and some of them are a whole lot better than 3 to 2. Some of them are 9 to 1 and beyond. Here's another picture. Now, your notes are different, so change them. I've thought that before, once I've got yours printed, I thought longer about this, and I've changed this primary secondary thing. Here's a slightly different view. Cyclopentadiene is underneath again. We're now sort of looking along the ketone as it's reacting so that we've got a better view of the orbitals, and I've chosen colours to show them. And of course the carbonyl pi bond is at right angles to the one that's technically reacting here. But a lot of the driving force for this reaction is the relationship between B and Y, and also between C and Y. So that's CY. This type of reaction only works with catenes, and it's because catene has this orbital of its own, the carbonyl has its orbital, and that gets involved. And if you think about it, that's the LUMO of the catene carbonyl group. That's its particular symmetry. The phase relationship between C and Y is that they are the same phase, and so there can be bonding interactions there, and that's actually a powerful driving force. Cyclopentadiene, remember, in its HOMO, the largest coefficient is on the terminus. The middle two atoms of cyclopentadiene, C values are slightly smaller. So that's the highest electron density in the HOMO of cyclopentadiene, and it's in proximity to the LUMO of the carbonyl group. And that's a powerful force, and I've decided that that's such a powerful force that it's actually a primary force in this type of reaction. So I renamed those things in your notes. So CY is a primary interaction. Heavily electron deficient, empty, quite well filled and electron rich. So that's a primary interaction. But it basically helps drag these other two olefin pieces together in the right 90-degree relationship that's required to get this S plus A reaction to occur. So this only works with catenes because they've got those green orbitals, in particular orbital C. And the small group points towards the reacting centre because the large group wants to be as far away from the action as possible. So that's the HOMO of the dienes reacting suprafacially. That's the cyclopentadiene. The LUMO of the catene is reacting antarafacially. So A and B are on opposite faces of that particular double bond. Antarafacial. Excellent reactions. I2S plus Pi2A thermally allowed, and it's because of this very odd transition structure which is enabled by the carbonyl and its electron withdrawing nature. Now, another allowed reaction is illustrated here. This is a Pi2S plus Pi2S, so superfacial, and it goes if you shine a UV light on it. I've done one or two of these reactions, and basically you have a large amount of ethene and a small amount of maleic anhydride, which is what that is, and you photolyse it, and one of the two components is photochemically excited. And it's that UV light which causes that, and that's what makes this reaction possible. And if you analyse the orbitals involved, as you must for this type of reaction, here's the ethene. Well, here's an unnamed ethene, X and Y groups. If we photolyse it in what this is representing the maleic anhydride part, if you shine UV light on this, then you can excite the energy level of one of the two electrons in the HOMO up to the what used to be the LUMO. And so after the photon has gone in, the new state is this electronic excited state, and there's one electron in this orbital here which was previously unoccupied, and so now the HOMO is this. And that is the orbital which will interact with the LUMO of the other reacting component. So here's our excited alkene 2, which put the UV photon into it, and we've excited the electron. It's gone into the pi star orbital. So that's the new HOMO. Here's the unexcited ethene in its ground state. There's its HOMO, there's its LUMO. So the HOMO-LUMO interaction, the key HOMO-LUMO interaction, is between this and this. And now there's a symmetry allowed overlap, because we've got opposite phases here on that face, opposite phases here on these two faces. And so when they get together, they can overlap simultaneously in phase, because they have the same phase properties. So that's the key FMO. And so the trick that we play in that is we excite one electron, we change which is the HOMO. The HOMO used to be that one. After UV's gone in, that's the HOMO. And now there's a positive relationship if we want to do synchronous overlap bonding, superfacial bonding. And there's the picture slightly differently. Alkene 1 is reacting superfacially, that's the ground state of alkene 1. Sorry, well that's its LUMO. Alkene 2 is reacting also superfacially, and that's its HOMO. I've called it HOMO star to differentiate it with its normal HOMO. And they of course have the same phase arrangement because they are actually the same orbital. So now that reaction is allowed, and those 2+2 additions work if you photolise, if you put UV light in. Now these reactions with UV light, it's not, I've glossed over, I haven't even mentioned the fact that UV light, although I've just studied and said, oh, you just photolise and it works, it's not that trivial to get a photon to interact with a compound. Of course there's got to be a wavelength overlap, you've got to resonate with its bonding energy, and that's why it's the carbonyl substituted part of that reaction that's the one that receives the photon. It's the devil's own job to get a photon to interact with ethene because the energy is so much higher. But once the carbonyls are on there, it's much easier. And so it's the maleic anhydride component most definitely is the one that becomes excited, not the ethene. And you can tell that because you get byproducts formed from maleic anhydride radicals. So it's clear that it's the carbonyl group, in fact, which is where the photon first goes. And that's how that process takes place. So when I blend, we say, oh, you just do it on photochemically instead of thermally. That can often be difficult. The actual process of making a photon interact with a molecule, don't just shine a light. Most of the time it just passes through. It has to be the right wavelength and the right sort of interaction. And there are tricks like sensitization and doing the reaction in acetone, and the acetone gets excited and that passes on the excitation. So photochemistry is not trivial, but having said that, that orbital argument is the one that's used to explain it. Now, I've dealt therefore with 4+2 and 2+2 cycloadditions, and you should now be seeing that there is a sort of selection rule appearing, and it's obviously based on orbital symmetry. The phase diagrams of these orbitals becomes more and more important. So far I've looked at these cycloadditions. 2+2 can go with heat provided it's supra plus antara. That's the ketene cycloaddition I showed you just a bit earlier, and the notation for that is pi2s plus pi2a. So that's a thermally allowed cycloaddition. 2+2 can go with light in a supra-supra manner. That would be a pi2s plus pi2s in the shorthand notation. 4+2, the deal's older. Those are thermally allowed, supra-supra. Pi4s plus pi2s, and you can actually do 4+2 cycloadditions with light, if provided you can get the photon to land in the right place. And that, if you did achieve that, then it would have to go supra antara. And so you could have a 4πs plus 2πa, or a 4πa plus 2πs. They would technically both be allowed. And I hope you can now see where these sort of selection rules come from. I'm going to widen that in a moment, but for now those are the selection rules that govern the 4+2 and the 2+2, and you've seen why. It's all down to the orbital interactions, and you can simply use the FMOs to predict. Frontier orbitals are the only ones you need to look at. HOMOs and LUMOs. That's what Fukui gave us. You could ignore the rest. This little graphic, I only really put it in because it took so long to draw. It's an attempt to show supra and antara slightly more clearly. So this frame is just a graphic trick to make you see what's in the front and what's in the back. So here's our orbital system. We're not defining. I want to open this out from 4+2, 2+2 to n electrons. And it doesn't matter how many you've got in your pi system, so that's an undefined pi system. These are the termini. And that component is reacting superfacially because the two terminal orbitals are both on the same side of that pi system. And this one is also another undefined pi pi system, and the two orbitals reacting are on the same face, and so that too is reacting superfacially. So that's an S plus S arrangement, and I haven't defined this time how many electrons. And if you want to have an S plus A, it's a more complicated diagram, and we've got to turn one of the reagents through 90 degrees and have it that the in-phase overlap is between these two which are superfacially arranged and those two which are on opposite faces of that pi system and are therefore defined as antarafacial. So that's another picture of how these selection rules are emerging. And you can see that I'm going to use extended systems as well. We've done 4 and we've done 2, but there's a whole load of more pi systems out there, and these terms are used to describe them as well. And so there's the table rewritten in a more general sense. Same principles, but I've changed, instead of specifying 4 plus 2, 2 plus 2, I'm just saying 4n electrons. And remember, that corresponds to a 2 plus 2 cycle addition. That would be a 4n, because there'd be 4 electrons. So I've extended this to larger systems, and I'll show you some of the phase diagrams that prove that this is right. So 4n, an even number of curved arrows in the mechanism, is another way to look at it. That helps to remember what sort of process you're in. In a 4n system, you're in the same place as the 2 plus 2. Heat, it's got to be S plus A. Light, it's going to be S plus S. In a 4n plus 2 system, such as the Diels-Alder reaction, which is 4 plus 2, so 6 electrons in that case, then that situation that applies in the Diels-Alder applies in the general term to 4n plus 2. This ought to remind you of Huckel. And in fact, one of the ways that pericyclic reactions are analysed is through Huckel analysis, where you have Huckel transition states and you have Mobius transition states. But these are harder to explain, visualise and defend than the FMO method. And there's a third method which I've mentioned on the sheet that I didn't mention verbally last week, which is the aromatic transition state, which is another way to look at it. And of course that's an aromatic number, that's an anti-aromatic number, and that's what gives rise to this connectivity, superfacial or non-superfacial. It's all linked up. So you've seen 4n and 4n plus 2 before. This is just its latest manifestation. But this, what really matters about this is what the rule is and how you use it to predict. That's what I want you to take away from the 6 lectures. How to use it. And you can predict it using, you can remember the selection rules from a table like this, and you know that you can go to frontier molecular orbitals, HOMOs and LUMOs, and explain it. And that's enough for me. So, phase patterns. I want to just finish by looking at some slightly more exotic phase patterns, but nothing that need containers very long. It's just a matter of agreeing that they are actually very easy to generate. We've done it with ethene and butadiene. Hexatriene is only adding 2 more. It's all based on linear combination, and it's all entirely predictable. So, in any given system, we're looking at the patterns now of the phases. In the HOMO and LUMO, if you compare for any one system, look at the HOMO and the LUMO, and you'll find that they have opposite symmetry. That's a rather general statement, I won't stick with it and won't define it for now. If the termini of the HOMO are in phase, then if we look up to the LUMO, we'll find that they're out of phase. And that's the key thing that's happening when we do this analysis of HOMO and LUMO. They always change phase relatively, going from one to the other. For adjacent systems which differ by 1 pi bond, so that's each time we add another 2 electrons to our system, the respective HOMOs have opposite symmetry. So if we have a 4 pi system and the termini in that are out of phase, if we make it into a 6 pi system, they'll be in phase. And that's also can be guaranteed. So these are the patterns that emerge if you sit in an idle moment and analyse the structures of all these 2, 4, 6, 8, 10, etc. pi systems. So, differ by 1 pi bond, the respective HOMOs have opposite symmetry. The termini of one HOMO are in phase, those of the adjacent HOMO are out of phase. And the LUMOs follow the same alternating pattern. Each time you add 2 electrons, the relationship between the end phases of the LUMO swaps over from being in phase to out of phase. So here's a picture with the simple LCAO done on 2 electrons, 3 electrons, 4, 5, 6 and so on. So we've got ethene here, seen before, butadiene, we looked at that last week, all in phase in Psi1, Psi2, Psi3, Psi4. That's butadiene anion or butadiene cation, depending on how many electrons you've got. Sorry, that's pentadiene, which will therefore have a radical or a plus or a minus at the end of it. So that's 5 orbitals. Here's hexatriene, all in phase, 3 in, 3 up, 3 down, 2 up, 2 down, 2 up. There's the HOMO, there's the LUMO. And notice again, in the hexatriene, in the HOMO, the 2 termini are the same face, on the same face, whereas in the LUMO they're in opposite. They're opposite. So it's that swap going same to opposite. That's the key to the change in behaviour. The requirement for light or heat is to do with the relationship between these end phases in the HOMO and the LUMO. And if we focus on that, which is what allows us to throw away most of these diagrams and just look at the HOMOs and LUMOs, the analysis we're doing is looking at these two and saying, are they in phase? And the answer is no. Are the end lobes in phase? No, they're not. In the HOMO, yes, they are. If we do that with 1,3-butadiene, are they in phase in the HOMO? No. Opposite. Are they in phase in the LUMO? Yes. And it's that no, yes, yes, no pattern that actually determines what can overlap with what. In hexatriene, the ends in Psi3, yes, they are in phase, so that's a yes. In Psi4, the LUMO, that's a no. And so you have to match reagents that have got the same word, yes or no, in those, I say match orbitals. So technically, you can see the value of this, I hope, which is that you can sit down and although we know that the Diels-Alder reactions work, we can predict that an 8+2 reaction should also work, whereas a 6+2 will not. 4+2, yes. We add 2, 6+2, no. 8+2, yes. So that's our 4n and 4n+2 rules, allowing us to predict. This is what happened in the 1970s when Woodward and Hoffman's rules came out. Everybody said, hang on a minute, this means that a 10+4 cycle addition must be allowed. Let's go and find one. And people went out and found them. And so I'm going to show you some really quite weird cyclode issues that people found in those days when you could just get money to do research simply because nobody had ever done it before. Whereas nowadays you have to be able to save the nation in the next 20 years. So, here are some of the politics over. Back to the chemistry. 4n+2 cycle additions are involved. Allowed reactions are superfacial about both components. And if 4n electrons are involved, allowed reactions are superfacial about one and antarafacial about the other. So those, I've just generalised the rules from 2+2 and 4+2 up to 2n, up to 4n and 4n+2. And I think that's where I'll leave it today.